Welcome back to the Scotti-BYTE channel, and this is Scott. Well, sometimes one of the best ways to understand where technology is today is to understand exactly where it came from. So in this presentation, I'm going to talk a little bit about the history of networking. So in 1973, Bob Metcalf and David Boggs at Xerox Palo Alto Research Center, otherwise known as PARC, invented Ethernet, which was a follow-on to the Defense Department's ARPANET in 1969. 6 years later, in 1979, Bob Metcalf left PARC Labs and co-founded a company called 3Com. In 1984, I was working at McDonnell Douglas in Houston, and I traveled to Palo Alto to meet with Bob in Palo Alto. So we discussed a design for an Ethernet network connecting all of the NASA Astronaut Training Division PCs, the Xerox 8010 Star workstations, and a VAX 11750, which I managed at the NASA JSC Astronauts Office. So the NASA Astronaut Training Division used AT&T 6300 PCs, which were 16-bit Intel 8086s running at 8 megahertz with 640 kilobytes of memory. Yes, that's kilobytes, which outperformed the IBM PC XT, which was only announced in 1983, which only ran at 4.7 megahertz. So the network used the classic 10-base-5 thick-net orange hose Ethernet, which had been standardized just a couple of years earlier in 1982. The cost of networking one PC with the 3Com 3C501 ISA bus network adapter with a TCL transceiver and a 15-pin drop cable was about $1,200. So this was really pretty expensive. Of course, about the same time, we spent around $3,000 to $4,000 for this class of PC as well. So the NASA network used Xerox XNS and Digital Equipment Corporation DECnet as the network protocols. So it was 1984, and the TCP/IP standard was only established in 1982, and it really wasn't the dominant network standard at the time. So the 10-base-5 cabling standard had a copper core covered by a white dielectric with a wire braid over the top of it, and then a paper sheath, and finally a plastic coating over the top of it. The paper sheath was orange, giving the cable its orange color. So most 10-base-5 Ethernet cable was manufactured by a company by the name of Belden, not Belkin, but Belden. And the cable looked like this. And it was really thick and it was really stiff. So the cable was delivered on really large, heavy wooden spools, and it was delivered in 500-meter lengths, which was the maximum length of an Ethernet segment at the time. And so there's an example of the spool. Keep in mind, this is a 10 megabit network, folks. 10 megabits was all we had. That was blindingly fast because the way we had connected PCs to host computers prior to this was with RS-232 cables, and we would typically extend those up to about 250 feet, and we'd try to run it anywhere between 2400 up to a high of maybe 9600 baud. And most everything we did was character cell oriented, which means it was terminal oriented because Windows didn't exist at the time, needless to say. So then both ends of the cable were fitted with a 50 ohm terminator, and that looked kind of like this. You'd put a connector at the end of the cable, and then you would screw one of these terminators onto it. So then we had a need for what was called a transceiver. So the 10-base-5 network was passive, meaning that it was just a cable and it didn't have any active electronic components as you're familiar with today. So today's networks are typically unshielded twisted pairs with active switches. You know, you plug a switch in, has a whole bunch of RJ45 ports, which look like oversized phone connections, and you connect your cables into it. Well, no such luck back then. So we used TCL transceivers, which were mounted on the 10-base-5 cable with a clamp, and then we drilled a hole with a special device into the cable to allow the probe on the transceiver to contact the copper core. And then the threads on the transceiver contacted the metal braid as they passed through the cable down to the core. So this is what the TCL transceiver looked like, and this right here was the probe, and they used to refer to these as vampire taps, and I think you can see why. And then this connector over here was the DB15 connector that goes back to a drop cable on that connected to the network interface adapter on the PC. So as far as network adapters, the 10-base-5 Ethernet cable could be up to 500 meters in length, as I mentioned already, and the network adapter connected to the transceiver via a DB15 connector, where the NIC also powered the transceiver itself. So the cable connecting the transceiver to the network adapter was called a drop cable. Now, drop cable was usually pretty flexible, but the Ethernet cable, not so much. So we used 3COM 3C501 network adapters in the AT&T 6300 PCs at NASA. We were some of the first people to use these adapters, and that's why I traveled over to Bob Metcalf's company 3COM to talk to him a little bit about the architecture, because we planned to build a fairly large network at the time, which was probably around 100 PCs or so. And this is what a 3COM 3C501 board looked like. You can see that it has a DB15 connector on the one side, and it also has a coax connector over here, and we're going to get to that here in a minute. So the 10-base-5 orange hose thicknet cable was extremely stiff and heavy. It had a turning radius of around 6 feet, and it was really hard to install in ceilings. I mean, we would open ceiling drop tiles and we'd try to push this cable up into the ceiling, and we didn't have a problem pushing it because it was relatively rigid. The problem we had was doing things like breaking ceiling hangers and overloading the ceiling and having ceiling tiles crack and fall in on us. So networking back then came with its fair share of risks, I suppose. So the 3COM 3C501 and other similar network adapters at the time also had that coax connector that I just pointed out to you, and that was an alternative to that DB15 connector that you saw. So that standard was called 10-base-2, or it was called thin wire Ethernet as opposed to thick wire Ethernet, and it could extend up to 200 meters, and it did not require a transceiver. So it was basically coax cable. And it looked kind of like this. You would have a coax cable running straight here, and then you would have a T connector, and this T connector would connect to the back. The reason this wasn't so popular in our configuration is because if somebody moved a PC or accidentally disconnected either this connector or this connector, all the machines on the network would immediately go down because it would lose termination and also lose continuity. So it wasn't a great way to solve things. It was a little less expensive. It was okay for a lab where you had 10 machines in the same room, but it was really pretty bad when you had multiple floors of a building or even an entire building covered. So then along came unshielded twisted pair, which is what we use today. So active Ethernet with switch technology using unshielded twisted pair was introduced, believe it or not, in as late as 1988 with the product that was called StarLAN by AT&T. And I think there was at least one or two other products at the time that also did the same thing. And the standard was just a little bit squirrely. They really hadn't come down to exactly how they were going to signal on the cables. So it really paid to select a vendor and stick with them. So I installed my first unshielded twisted pair, or otherwise known as UTP Ethernet, in 1990, and it was from a company called Synoptics Communications, and the network was called LatticeNet. And I installed it at a McDonnell Douglas office just outside the Washington, D.C. Beltway. So UTP Ethernet made cabling a lot cheaper, and the initial technology was referred to as 10-base-T to denote twisted pair. So if a 10-base-5 thick wire network had to exceed 500 meters, we installed an active repeater to connect to another 10-base-5 segment. And then back in that time, well, we didn't have NAT, which was invented in 1994 through RFC 1631. So as a consequence, all of our systems were directly connected to the public internet. And I've got some great stories about how we had some security compromises, but back then there weren't very many people on the internet, and hacking or being unethical was virtually unknown in regards to the use of computers for the most part. So we achieved different network address ranges with very expensive computers, which we called routers, but they're not routers in today's sense because they didn't have anything like firewalls or any of the great tools we have on today's routers, but they had multiple network adapters where each adapter provided one address range to a network of devices. So typically imagine there would be a 10-base-5 segment behind adapter 1, another one behind adapter 2, and each one of them may have a different address range, and it was that computer's job to do the routing between those networks. So everything was statically addressed, by the way, since DHCP was also not defined as an RFC until late 1993. So you had to be very careful in your address assignments and make sure not to reuse any addresses, or else you'd have conflicts on the network. So then along came virtual networks. So in 1998, VLANs were described in IEEE 802.1q, which is commonly referred to just as .1q. And a virtual local area network, or a VLAN, is a unique address range that is logically, rather than physically, isolated on your network at OSI layer 2, which is the data link layer of your network. So .1q makes what it does possible by adding a 32-bit field inside of an Ethernet frame, which is called a VLAN tag. So VLANs require a managed router and also managed switches to create and manage VLANs. So on a LAN, the main address range is referred to as the untagged VLAN, which by convention is sometimes called VLAN 1, but we generally call it just the untagged VLAN. So that would be your main network address range. So for those of you that either have managed networks or unmanaged networks, you might be using 192.168.1. whatever, and that would be called your untagged LAN. So a layer 3 router handles subnets and IP address routing, and IPv4 subnets are broadcast based. So the reason it's important that they're broadcast based is because VLANs are also used to isolate traffic for performance reasons, and since IPv4 addresses are IPv4 subnets are broadcast based, if you have them divided into multiple subnets, then you end up having less traffic on each subnet because there's less machines that have to report in. So a layer 2 switch, otherwise known as a bridge, if you watch my channel very often, you know that I tell you that a switch is also a bridge, and a bridge is also a switch. And it handles VLANs and MAC addresses. Multiple VLANs can be implemented on a single cable, and that's very important. You can have 10 VLANs on one cable, and you can even have multiple VLANs on the same Ethernet adapter. And that's something else I cover on the channel frequently, where I've had 2 or 3 VLANs on one network adapter on one host machine, say on one VM or on one LXD instance. So valid VLANs can be created and they're numbered from 2 to 4096. And as I mentioned, VLAN 1 is kind of reserved. And then also, well, if you're on a Cisco network, Cisco reserves VLAN numbers 1002 to 1005 for fiber distributed networks, FDDI, and token ring networks, which of course were an IBM network type. And then ports on a switch can be configured to use a single VLAN profile, and the connected computer will communicate on the VLAN. If a switch port profile identifies multiple VLANs, the connected computer must create a virtual adapter to connect to the desired VLAN. So for a computer to use a VLAN, it must first be created on the managed router. A managed switch is required to manage VLAN port profiles. And Windows, Mac, and Linux all support virtual Ethernet adapters to connect to the VLANs defined on your network. Wireless connections to VLANs are simple if your wireless access point supports VLANs. And that would be called a managed access point, by the way. So you would connect the AP, the access point, to a managed switch port with the port profile allowing all VLANs, assuming that you wanted to have SSIDs in more than one VLAN. Because if you set the port that the AP is connected to be a port profile for one VLAN, the access point will only be able to access that one VLAN, if that makes sense. So the next step is to create an SSID designating your tagged VLAN number that you want that SSID to communicate with. And the wireless client talks to the AP, so in other words, a phone or a tablet or a laptop, and it bridges it to the managed switch port, and its traffic is relayed to the router, which grants a DHCP address and gateway according to how you set up those values in the VLAN. So an address would be granted within that particular VLAN. And then for self-hosting, wired managed connections are a best practice, and wireless VLANs are really only suggested for client-based systems. So for a best practice, I like to create VLANs with a 24-bit mask that use the VLAN number as the third octet. So as an example, say 192.168.30.0 and a subnet mask of 24, which is effectively 255.255.255.0 would be my VLAN 30. So I can see the 30 is the third octet and I know it's VLAN 30. That's a way to self-document what I've got, and that's something I believe is a best practice. Not required, just a good thing to do. And then most of the complexity with VLANs comes with deciding how traffic should be routed. In my home lab implementation, I allow my main untagged LAN to talk to any of my VLANs. I allow my VLANs to respond to requests that come from the main LAN. My VLANs are not allowed to initiate access to other VLANs or to the main LAN. And this is what provides isolation for security and traffic segmentation for performance purposes and also obviously security. I guess I said that. So in Windows Device Manager, you can create a virtual adapter to talk to a VLAN. You go into Device Manager, you go to your particular network adapter, you go to the Advanced section, and they have an option to set the VLAN number. And when you set the VLAN number, it will actually create a virtual VLAN adapter on the machine, which should get an IP address on that VLAN from the DHCP server on your router serving that VLAN. So this will create a virtual adapter for that VLAN, as I mentioned previously. So in Linux, you may or may not have to do this, but it's certainly a prerequisite if it's not already there. You would have to do from the command line a sudo apt install VLAN, and that's the VLAN component, so it understands VLANs. And in order to create a virtual NIC to connect to VLAN 30, if your physical adapter is, say, named EMP4S0, and you would do that by looking at your Ethernet adapters with something like an ifconfig, you would do the command sudo IP link add link EMP4S0 name EMP4S0.30. By convention, they usually put a dot and then the VLAN number after it to name it so it reminds you what it's talking to. And you say type VLAN ID 30, and that's all there is to it. So all routers are different. All managed routers provide a different way to create and manage these VLANs. There really is no one particular way. And on the channel before, I've covered how this is done on Ubiquiti Unify routers, since that's what I've got here. But for example, in pfSense, the way you would do this is you would go to select interfaces and then go to assignments. In the assignments section, you'd select VLANs and then add to add a new pfSense VLAN. In the parent interface, you would select the LAN interface that you have configured. And the VLAN has now been created in pfSense. So in summary, Ethernet networks are barely 50 years old. Bob Metcalfe and David Boggs are the pioneers of the networks that we're using today. And VLANs are only about 25 years old. However, Windows, Mac, and Linux all support VLANs out of the box, and you can create VLAN virtual devices for them to communicate. And VLANs are good for security as well as traffic management. So I have several videos on the channel that describe the use of VLANs on Linux and Windows using virtual machines, LXD containers, and Docker. And if you go out and search the channel, I have a lot of really detailed videos talking about how they're used exactly. Anyway, that's it for today. Please subscribe and like to the channel, and don't forget to hit that notification bell, and we'll see you next time.